Right now, in the middle of the Gobi Desert, in one of the most remote and empty places on Earth, there is a machine quietly humming that could change the future of energy for the entire planet. It does not run on uranium. It does not use the fuel that every nuclear power plant you have ever heard of depends on. It runs on a soft, silvery metal so common that we often throw it away as mining waste. A metal there is enough of to power human civilization for thousands of years. And here is the part that should stop you. The blueprint for this machine was not invented in China. It was invented in the United States over half a century ago. America built it, tested it, proved it worked, and then abandoned it, buried the research, walked away. China just picked those abandoned documents up, finished what America started, and switched it on. Look at this is the story of the most important energy technology you have probably never heard of. A technology that was left for dead in an American archive for 50 years and has now roared back to life in a Chinese desert. To understand why this matters so much, you first have to understand the metal at the center of it all. Because once you understand thorium, you'll start to wonder why we ever walked away from it in the first place. Let me introduce you to thorium. It is a naturally occurring radioactive metal named after Thor, the Norse god of thunder. It is silvery, it is slightly radioactive, and it is remarkably abundant. It is found in the Earth's crust roughly 3 to 4 times more commonly than uranium. It is scattered across the planet, and enormous quantities of it are pulled out of the ground every single year as a waste byproduct of mining for rare earth element. Decide we no use for it and pile it up as waste. Think about that for a moment. One of the most energy-dense materials in the universe, a substance that could power entire nations, is currently treated as garbage. In some places, it is considered a disposal problem, an unwanted radioactive leftover that mining companies have to figure out how to store safely. Again, when I say energy-dense, the scale is hard to even picture. The amount of energy locked inside a single lump of thorium the size of a golf ball, if fully used, could in theory supply all the energy a single person needs for their entire lifetime. Their heating, their electricity, their transport, everything from a piece of metal you could hold in your palm. That is the almost magical density of nuclear fuel, and thorium delivers it while being far more abundant than the uranium we currently rely on. And here is the number that makes this almost unbelievable. Some scientists estimate that a single thorium-rich mine in Inner Mongolia holds enough of this metal to meet China's energy needs for thousands of years, not decades, thousands of years, from what is essentially a pile of waste. So if thorium is this abundant, this powerful, and this widely available, the obvious question is the one you are already asking. Why is the entire world not already running on it? Why have you never heard of it? Why does every nuclear plant on Earth run on uranium instead? The answer to that question is one of the strangest and most consequential decisions in the history of energy, and it takes us back to America in the middle of the 20th century. In the 1950s and 1960s, at Oak Ridge National Laboratory in Tennessee, American scientists were pioneers in nuclear energy, and a group of them, led by a physicist named Alvin Weinberg, became convinced that they had found a better way to build a nuclear reactor. Not with solid uranium fuel rods submerged in high-pressure water, the design we still use today, but with something radically different, that used thorium dissolved into a bath of molten salt. They actually built it. They ran an experimental molten salt reactor at Oak Ridge, and it worked. It ran for thousands of hours. It proved the concept was real. This was not a fantasy or a theory. It was a functioning machine over 50 years ago that demonstrated a cleaner and safer path to nuclear power. To understand why they were so excited, you need to understand what a nuclear reactor fundamentally is. Strip away the complexity, and a reactor is just a very sophisticated way of boiling water. That is genuinely it. Radioactive material generates intense heat as its atoms split apart. That heat boils water into steam. The steam spins a turbine. The turbine generates electricity. Every nuclear plant on Earth at its core is a high-tech kettle. The differences are all in how you generate and control that heat safely. And the Oak Ridge scientists realized that the standard method, solid uranium rods in pressurized water, carried risks that a liquid thorium design could simply avoid. They were not tinkering at the edges. They believed they had found a fundamentally better architecture for a machine, and then the United States shut it down. Now, why would a country abandon a working clean energy technology? The reason is uncomfortable, and it tells you a great deal about how the modern world was shaped. The decision was not really about which reactor made the best electricity. It was about weapons. This was the height of the Cold War, and the uranium-based reactors had a feature that, from a military standpoint, was not a flaw at all. They produced plutonium as a byproduct, and plutonium is the core ingredient for nuclear weapons. A nation building a fleet of uranium reactors was also, conveniently, building the industrial base to produce material for an atomic arsenal. Thorium reactors did not offer this. They were much worse at producing weapons material. From the perspective of a clean energy scientist, that is a wonderful thing. From the perspective of a Cold War government racing to build bombs, it was a reason to look elsewhere. The uranium path gave you power and weapons in a single package. The thorium path gave you only power. So the money, the talent, and the political will all flowed toward uranium. The thorium research at Oak Ridge was defunded and eventually shut down in the early 1970s. Alvin Weinberg, who had pushed for the safer design, was effectively pushed out of the very laboratory he had led. His warnings about the safety advantages of his design went unheeded because safety was not the priority of the moment. Winning an arms race was. Sit with the strangeness of that for a second. The reason your home is not powered by a thorium reactor today has almost nothing to do with whether thorium is good at making electricity. It is good at making electricity. The reason is that 70 years ago, the world needed bombs more than it needed clean power, and it chose the technology that made both. Every uranium-clean tower you have ever seen is a monument to that Cold War decision. And one of the most promising energy technologies of the century was packed into boxes, written up in reports, and left to gather dust. Up here is the crucial detail, the one that sets up everything that follows. When the United States shelved this research, it did not lock it away forever. Over time, those documents were declassified. The reports, the experimental data, the hard-won knowledge of worked and what did not were made publicly available. America published its abandoned homework and left it on a shelf for anyone in the world to read. For decades, almost nobody did anything serious with it. The knowledge sat there, open, waiting. And then China walked in. In 2011, the Chinese Academy of Sciences launched a serious, well-funded program to build a thorium molten salt reactor. They tasked a scientist named Zhu Hongji with leading it, and his team did something that is both humble and audacious at the same time. They went and found those declassified American documents. They read them. They studied every page. They located the old Oak Ridge experiments to make sure they understood exactly what the Americans had learned. And then, in Zhu's own words, they mastered every technique in the literature and then pushed further. One of the phrases used to describe this is striking. The Americans, Zhu suggested, had left their research open to the world, waiting for the right successor, and China decided it would be that successor. The scale of the effort was enormous. Construction on their reactor began in 2018. The research team grew from a few dozen people to over 400. Many of them relocated to a remote site in the Gobi Desert and stayed there for most of the year, skipping holidays, living beside the machine they were building. This was not a small side project. This was a national mission. Again, the choice of the Gobi Desert was deliberate. It is remote, geologically stable, and bone dry, which makes it ideal both for a nuclear facility and for the long-term storage of little waste the reactor produces. China was not just building a reactor, it was building an entire ecosystem around this technology in a place chosen to support it for the long haul. Over $400 million has been invested in the program since 2011. This is the behavior of a country that has decided, at the highest level, that this technology is worth winning. And it worked. In October 2023, their thorium reactor went critical, meaning it achieved a sustained nuclear reaction for the first time. By June 24, it reached full operational power. And then in 2024 and confirmed in 2025, they achieved something that no one, not even the original Americans, had ever done. They reloaded fresh fuel into the reactor without shutting it down. That last achievement might technical, but it is the key to every two-year thing, so let me explain why it matters so much. A conventional nuclear reactor has to be shut down to refuel. You power the whole thing off, open it up, swap out the solid fuel rods, and start it back up. It is a slow, expensive, disruptive process. But because a molten salt reactor uses fuel that is dissolved into a liquid, you can, in principle, add new fuel and remove waste products continuously while the reactor keeps humming along and generating power. No shutdowns, no interruptions. A reactor that could, in theory, run continuously for very long stretches of time. Proving that this could actually be done in a real working reactor is what makes this a genuine world first. It transforms thorium molten salt reactors from an interesting laboratory curiosity into something that looks like a practical continuous power source. So now you understand what is humming away in that desert, but you might still be wondering what makes thorium and molten salt so much better in the first place, and the advantages are genuinely remarkable. We'll start with safety. This is perhaps the single biggest reason to care. Think about the nuclear disasters that live in our collective memory. Chernobyl, Fukushima, in both cases, a core part of the catastrophe of intense heat and pressure and the risk of a meltdown when cooling systems failed. Traditional reactors operate under enormous pressure and they rely on constant active cooling to avoid disaster. If that cooling fails, things can go very wrong very fast. A molten salt reactor works completely differently. The fuel is already dissolved in liquid salt, and the reactor operates at normal atmospheric pressure, not the extreme high pressure of a conventional plant. This alone removes an entire category of catastrophic failure, and there is an elegant safety feature built right into the physics. Many of these include what is called a freeze plug. If the reactor overheats or loses power, a plug at the bottom simply melts liquid fuel yield, drains out by grind into a holding tank where it spreads out, cools down, and the reaction naturally stops. No intervention required. No frantic pumping of emergency coolant. The laws of physics themselves shut it down. Then there is the waste. One of the most powerful arguments against nuclear power has always been the radioactive waste, the material that stays dangerous for tens of thousands of years and has to be stored and guarded for longer than human civilization has existed. Thorium reactors dramatically reduce this problem. They produce far less long radioactive waste than uranium reactors. The waste they do produce is generally less radioactive and decays over a much shorter time scale. It does not eliminate the waste problem entirely. And I want to be honest about that, but it shrinks it enormously. Again, then there is the weapons issue turned on its head. The very reason America abandoned thorium, that it is bad for making bombs, is now one of its greatest selling points. In a world terrified of nuclear proliferation, a reactor design that generates clean power while being very difficult to weaponize is not a drawback. It is exactly what a peaceful energy future would want. The flaw became the feature. So let me be fair and honest, because this is not magic and no honest story pretends otherwise. Thorium molten salt reactors face real challenges, and they are significant. The biggest one is corrosion. Molten salt at extremely high temperatures is chemically aggressive. It eats away at the materials of the pipes and containers that hold it. Building a reactor that can survive being filled with hot, corrosive, radioactive salt for years or decades is a genuine materials science challenge, and it was one of the problems that helped stall the original American research. There is also the complexity of handling the fuel. Because it is a liquid that is constantly circulating, you have to continuously process it, removing waste products and balancing the chemistry, all while it is intensely radioactive. This is difficult and delicate work, and the waste, while reduced, still has to be managed. China plans to store its reactor waste deep underground in the stable, arid geology of the Gobi Desert. These are not trivial problems. They are the reason this technology took so long to reach this point. But the crucial thing is that China appears to be systematically solving them one by one in a real operating reactor rather than in a theoretical paper. Again, they are not stopping at one small experimental unit. The current reactor is a small prototype generating a couple of megawatts of thermal power, but China has announced plans to scale up rapidly. A larger reactor is targeted for the coming years, and commercial-scale reactors generating 100 megawatts are planned for around 2030. They have even announced the intention to build enormous container ships powered by thorium reactors, which could dramatically cut the carbon in they're trying to close to 80 millions of carbon pollution. Every container ship's alone pollution every year. By compact thorium reactors would rewrite the emissions math of global trade itself. And underneath all of this is a strategic prize even bigger than clean air: energy independence. China currently imports vast quantities of oil and gas, much of it through sea lanes that could be cut off in a conflict. A nutting tower for thousands and already has sitting in its own deserts is a nation that can never be strangled by an energy blockade. This is not only an environmental story or a scientific story, it is a story about power in every sense of that word. Step back and look at the whole picture, because it is genuinely stunning. A technology invented in America and abandoned for its inability to make weapons. Declassified and left on a shelf for half a century. Picked up by a rival nation that read the abandoned research, replicated it, improved it, and switched on the world's first working version in a desert. And that nation is now racing toward using it to power its cities and even its ships. There is an old saying that gets used to describe this exact situation. The tortoise and the hare. America was the hare. It sprinted ahead and invented the technology and then, distracted by other priorities, stopped running and rested. China was the tortoise. Slow, patient, methodical, picking up exactly where the hare had quit and walking steadily across the finish line while the hare looked the other way. Whether thorium truly becomes the clean energy future that its supporters have dreamed of for decades, we do not yet know. The challenges are real, and scaling any nuclear technology is a long and difficult road. But something profound has happened here. A door that America closed and forgot about has been reopened. And the world may be about to discover that the answer to one of its biggest problems, clean and abundant energy, was written down over 50 years ago, set aside, and left in the dark for someone with the patience to finish the job. It makes you wonder what else is sitting in some forgotten archive right now. What other solutions have we already discovered, proven, and then walked away from simply because the timing or the politics were not right? The machine humming in the Gobi Desert is a reminder that sometimes the future is not something we have to invent. Sometimes it is something we already invented, abandoned, and simply have to find the courage to switch back on. If you find these hidden and forgotten breakthroughs as fascinating as I do, subscribe, because there is far more of this story to come, and the world is changing faster than anyone realizes. Again, tell me what you think in the comments. Did America make a historic mistake by walking away from thorium, or was it the right call at the time, and China is simply the one lucky enough to finish it? The most thoughtful answer gets pinned.